All right. Combinatorics, chapter 9. Chapter 9. Uh, this is exciting. Again, if this stuff doesn't get you going, well, I'm sorry. I'm doing my best here. I'm doing my best. So the first thing I want to talk about is the individual that is the inspiration for what we will be discussing in chapter 9. I'm always trying to sprinkle in a little bit of historical context. So I'm going to pull this up here. This is the guy right here, George Polya. He's from the Hungarian School of Mathematics. There was kind of a renaissance of combinatorial thinking during like the First and Second World War era, and he was right in the middle of all that. Amazing mathematician who really had his fingers in a lot of areas, not just in combinatorics, but also in probability theory, number theory, numerical analysis. He was friends with, one of the most famous Hungarian combinatorialists was someone by the name of Paul Erdős, very famous. Erdős, that's E-R-D-O with an umlaut S, but George Polya would have known him well. And he had his hands in kind of applications of combinatorics in the area of biology and chemistry. And so he was interested in how to count things that involve, like molecular arrangements of certain kinds. He was really interested in so-called isomers. Like sometimes you'll have different atoms, ATOMs, bond to each other, and the way in which they bond to one another can affect the molecular composition and the properties that it possesses. So sometimes you can have different isomers that consist of the same atomic structure, but the way in which the bonding occurs can affect the properties of that molecule. Those are different isomers of the same molecule, okay? And so that's why what we're going to talk about today is kind of a big deal. I mean, look, in general, I just want to say this just from one mathematician to another. If you continue in this business long enough, people will start to question you, and they'll say, okay, why are you talking about all of this abstract nonsense? It's clearly has no applications. And what I've learned, I used to try to come up with all these, like I would think and go, oh man, how does this really apply? And I would have to come up with all kinds of stuff. And what I've learned is, well, wait a minute. That's been said lots of times in the past, and it has turned out not to be true at all. Okay, there's example after example of that in the mathematical folklore. So when someone makes the claim on the front end that clearly what you're looking at has no applications whatsoever, they're claiming some kind of omniscient perspective. That is, that they know that it's not useful now and therefore never will be. That's just untrue. A lot of abstract number theory was totally useless at the time, and it turns out now it's one of the most useful things of all, undergirding a lot of cryptography, for instance. Another example would be imaginary numbers. Complex analysis was always seen to be just utter foolishness until Raphael Bombelli in the 16th century used complex numbers to find roots of a polynomial equation that were actually real, that you would not have been able to find had you not been willing to go through the complex numbers. So that's It's amazing. And it was that moment that people were like, oh man, maybe we better try to understand imaginary numbers better. Okay. And there are just numerous examples of situations like that. Go talk to Dr. Fry, who really doesn't care if his stuff has any applications, and neither do I, frankly. But he was contacted by some string theorists at Harvard, and they were like, hey, tell us about the Leach lattice. And he goes, okay. And he did it, and they wrote a physics paper together, because apparently some of the stuff he did that was just complete abstract nonsense ended up being useful in the realm of string theory. And even if even if something doesn't ever end up being useful, well, who cares? It's still interesting. It's invigorating. It's true. And as believers, we ought not be prone to ask those kinds of questions. We know that it could be useful, and even if it never is, it brings glory to the Creator. So that's just a little integration of biblical thinking there. Okay, so we have Polya. Okay, and what I want to do is, hang on a second here. I need to share this screen. So there we go. Polya enumeration. Okay, and again, we're just going to be primarily interested in counting the number of configurations that are basically equivalent. For those of you that took number theory with me, we saw something kind of like this when we went to prove something called Fermat's little theorem. We had a little bracelet configuration situation. We're trying to count the number of basically equivalent bracelets if we allow it to float in two-dimensional space freely, kind of rotate around. And we're going to be doing that here. Okay, so Polya's enumeration formula will be the ultimate goal, but we'll have a little bit of work to do before we get there. Okay, so the goal is that we want to determine the number of, at first it's just going to be 2 colorings, okay, which is the easiest to do in this setting, because all I have is black and white available, really. Well, that's not totally true. I could do other colors, but that was easiest to do in LaTeX. Determine the number of 2 colorings of vertices of a cube or a tetrahedron or icosahedron, and we're going to allow it to kind of float in 3-dimensional space freely. Okay, so it's going to be floating around freely. Okay, that means some things are really not different from other things, and we'll see what I mean here in just a minute. That makes it harder to count the number of distinct things, because you need to know how many of those things float into each other, really. So are basically the same. If we didn't allow floating, the answer would be easy. You would just go to each one of the vertices, and the total number of colorings would just be 2 to the number of vertices, because you have 2 colors, black and white, and you have 2 choices for each vertex. 2 times 2 times 2 times 2, a total of the number of vertices times. Okay. So down here, we're gonna actually, as our kind of running example, and this is the one they use in the book, if you want to follow along. 2 colors. We're gonna color the square. Okay. We're going to color the square, the vertices of the square. Of course, the square has 4 vertices and 4 edges, actually. And there are 16 total colors, because 2 to the colorings, there's 2 to the 4th if we fix the vertices. But we want to count how many of these colorings are actually the same thing eventually. But for now, we're going to go down and define these colorings. Again, I'm just bear with me. There's going to be a lot of things that we have to set up in order to get somewhere with this, and that's that makes it sort of intense. So again, let's label these colors. I've labeled them down here. These are also in the book on page 356 in my copy of the text, figure 9.1. I basically have just copied those colorings, just so all of my note taking is consistent with what's in the book, and you can kind of follow along. Okay, so one coloring is like where all the vertices are black. That's what I call C1. But C2 like has one vertex in the upper left that's white and the others are black. C3, you can see that the white vertex has moved over to here. That's the third coloring, the fourth coloring, the fifth coloring. Notice I've kind of blocked this off up here into this upper right. Why? Well, essentially, this color, I can get to this one, but into this one, into this one, I can get all of these by simply rotating this coloring C2 by 90 degrees over and over and over again. So if I allow it to float, I can get all of those things, okay? And again, we'll say that two colors are equivalent to each other, and this is what Polya would have been interested in. Two colorings are equivalent to each other, and we write this little twiddle to mean equivalent. Ci is equivalent to Cj if and only if there's some way that we can float Ci into Cj, and we'll definitely make this more precise later. There are basically 6 equivalence classes and, of these 16 colorings, okay? And I've split it up accordingly down here. So like C2, C3, C4, C5, these are all equivalent to each other. If you just simply think of these things rotating into one another. These guys right here, what's the deal? C6, okay? C6 has these 2 white vertices and 2 black vertices down here, but of course, you know, I can rotate C6 by 90 degrees to get C7, and then continue to rotate by 90 degrees about the center. And I'm just going to keep going around in these guys. So these guys are basically equivalent through this floating that we're thinking about. C10 and C11, you know, you can see the same thing. Now the white vertices are on the corners and the black on the opposite corners. C12, here I have 3 white vertices and 1 black, and I rotate that thing around. So these 4 are float equivalent to each other. And then C16 is the one with all white vertices, okay? So that's kind of the setup here for what we mean by equivalent and what we mean by floating. And we'll make this way more precise here pretty soon, okay? So I'm just going to warn you, I don't exactly, I don't love the way that the book sets up this situation, okay? I don't love it, but I'm going to go with it because I want you to be able to understand what's in the book, okay? It's kind of like the situation I said where they eliminate the intersection symbols. I didn't like that either, right? I whined about that a lot. Well, I think that some of the notation is clunky that they choose because it's hard to remember some of these things. That's the main hindrance, but I'm going to use what they say, okay? So first of all, how is it that okay, just as human beings, we can kind of tell this is an equivalence class unto itself. This is an equivalence class unto itself. This one, these 2 guys, these 4, and this one right here. So what we originally thought were basically 16 distinct colorings really aren't 16 distinct colorings. You see, they're not really distinct. There's really only 6 distinct colorings, okay? But it seems like something really complicated is going on because some of these equivalence classes have 4 things, some only have 1, and some have 2. Are you kidding me? But how are we going to count these things? we really want to get an answer of 6. We want to get an answer of 6, but right now it's like there's 16, and we're trying to develop a general theory here that will allow us to count to get that number 6, okay? Just based on the structure of the thing we're looking at. So let's talk about the symmetries that give rise to these equivalence classes of colorings, these 6 equivalence classes. Okay, so there are 8 symmetries of the square, and all of them are labeled in the text. You know, if you look at the top of page 357, they have some nice pictures. I'm going to just describe them to you here. But the notation I've chosen is absolutely consistent with what's there in the text. Pi 1 is the identity. That's the that just is the operation that leaves the square alone. Pi 2 is rotation in the clockwise direction. That means to the right. Is rotation to the right by 90 degrees. So that's what pi 2 is. Rotation to the right in the clockwise direction by 90 degrees. So that's what we were applying over and over and over again here. That, you know, we apply pi 2 to C2 to get to C3. We apply it again to C3 to get to C4, etc. Pi 3 is rotation by 180 degrees. And that's basically pi 2 applied twice. Like you apply 90 degrees and then you do another 90 degrees. So pi 3 is rotation by 180 degrees. So for instance, if I applied pi 3 to this coloring C2, I would get C4. And if I applied pi 3 to C3, I would get C5. If I apply pi 3 to this coloring C4, it would go back to C2, yes? 180 degree rotation is what pi 3 is. And pi 4, what do you think that is? Well, that's 270 degree rotation. And then pi 2, you can almost think of that as 360 degree rotation, but that's really like not doing anything. Okay, so that's what those guys are. Oh, and by the way, pi 4 is 270 degree rotation. So that means like C2, that this white vertex would go to this one down here, which means I'm basically here. But that's also the same thing as going backwards by 90 degrees. So that's going counterclockwise by 90 degrees. Okay, that's what pi 4 is. Pi 5 is reflection in the vertical axis. Pi 5 is reflection in the vertical axis. So that's this axis. Okay, so it kind of flops back and forth, like it takes these. It's kind of like, remember, we're thinking about this thing as floating, right? Floating. So it's going like this in 3-dimensional space. That's what's happening. That's what pi 5 is. Reflection in the vertical axis. Pi 6 is reflection in the horizontal axis. So it's like this. Yep. Pi 7 is the negative slope. Pi 7 is the negative slope reflection axis, which means like this right here. Negative slope. I can reflect across that, so that would just flop these two vertices back and forth. Of course, if I apply that one, so what is that? That's pi 7. If I apply pi 7 to this one, then those two vertices don't go anywhere, and these two flip back and forth. But of course, that doesn't do anything to C13, right? If I apply pi 7 to C13, I just get C13. But on the other hand, if I apply pi 7 to C14, I do get something different, because these two would get fixed, but these would flop back and forth. If I apply pi 7 to C14, I get C12. You see that? It's going to go like that. Okay, so that's interesting. Okay, and pi 8 is the positive slope reflection. So I go, you know, I reflect, I draw the line like this, and I reflect these guys across from each other. So pi 8 is going to flip these two guys back and forth, and so that would tend to toggle us between the 13th coloring and the 15th coloring. Okay, so there you go. That's like the 8 things that can happen with the square. And you know what? This is getting kind of lengthy. I don't know if I want to get into the details of this stuff down here just yet, but the setup is fairly involved here. But I want you to have the general idea of what's happening with the equivalence of these colorings, you know, and just grasp the complexity of what it is we're counting, namely these 2 colorings of vertices, but we want to allow these things to float around, okay? And in so doing, we realize there's not really 16 or 2 to the 4th distinct colorings. There's really only 6, okay? And what we're going to do is we're going to take these rotations and reflections of the square, and we're going to let them operate freely on these colorings. And we're going to use some properties of these rotations and reflections to tell us flat out how to get the number 6 from those. Okay? And it will be some amazing combinatorics that we will see transpire. It's going to be exciting. That's going to require a little bit more abstraction. From where we are right now. Okay, so I'm going to stop this right now, but there's some exciting times ahead for us. That's it for now.